Okay, we know what Green's theorem says globally, right? We just have any closed curve, and we get to do that with a double integral around S, and we have what we've been calling the two-dimensional curl function. So this is partial f2 with respect to x minus partial f1 with respect to y dx dy. That's what it would mean locally. I'm sorry, that's globally. Now what I want to do is focus on just a little tiny piece with a little tiny area and a little tiny curve around it. So now just think of C as being little tiny, the region being little tiny, the area being little tiny. Now, why would this make any difference? Well, it still says that the work done around our little tiny curve is equal to the double integral of all that, taking our time and just writing it out, because we're going to look at the right-hand side and remind ourselves what the definition of this is, right? Remember what the definition of any double integral is, right? Is that you look at the region, you break it up into little tiny rectangles, you draw a French fry, right, above that little tiny rectangle, and you get a little tiny volume, and then you add up all the volumes of all the French fries, you get a slice, you add up all the volumes of all the slice, you get a whole potato. When you take the limit, you get the whole volume, where this funny vector function here is the roof. However, if the region is really, really small, and you're going to see this in physics and chemistry books, if the region is really, really small, then we can estimate that entire integral with just one French fry. So what we do is we say this whole integral, because the region is so small, is that we can estimate that with one French fry. Now what we do is we pick any point in that little tiny region that we want, we plug it into this function, that'll give us the height of the French fry. Now the region is so small, right, that we don't actually care that it's delta x, delta y. What we do care is that it's just the area of the bottom. Now this only works if the curve is really, really tight and the region's really, really small, but this is actually very much how Green's theorem is, the function of Green's theorem is actually used. Because if we have a teeny tiny region and a teeny tiny area, that we can calculate the work done around that by just plugging in one point, multiplying the area by the area of the region, and getting the work done as the answer. So that's what Green's theorem implies locally, that if we have a really small region, we can get the work done around that really small region just by multiplying the curl function by the area of the region.